today we're going to talk about training a small language model, like kind of the process. We're going to do kind of cover language models 101, all the things you need to know, and we're going to do that in a non-PhD style so that it's accessible for everyone. And we're actually going to cover 3 different types of language models. So let's go ahead and get started. So my name is David Von Thenen. I'm an AI ML engineer at NetApp. So I've kind of been doing the AI ML thing for like some time now. I have an interesting background. So I kind of started out in enterprise storage, then went into large-scale backup recovery solutions for virtualized environments, did open source Kubernetes, which is where I went into like dev advocacy and open source. And then kind of like roughly 5 years ago, I was like, hey, I heard this AI was going to be a thing. And then kind of made the jump into that. And that's kind of where I'm at here today. So hopefully we'll take a look at small language models. And this is the agenda. So we're going to do small language models 101. So like what are some of the terms that you probably hear when it comes to like training and how large language model, and also by extension how a small language model works. Then we're going to talk about discussing how to build a small language model from scratch. We're going to do a live demo, obviously not the training because that would take way too long. And then we're going to talk about doing it the right way in terms of fine-tuning and quantizing a model. And then as kind of a bonus, I kind of thought I'd throw this in here. There are many different types of small language models or language models in general, and we're going to pick one that I've built, and we're going to go ahead and take a look at that. And we'll do 3 live demos and have some Q&A at the end. So, small language models 101, the basics and the process. So, by a show of hands, who here has used like OpenAI, Claude, some large language model? Okay, a ton of people. That's not surprising these days. A small language model is exactly like a large language model. You know, you have processing, you have some natural language context understanding, and then you're generating some natural language content, right? Some language in, processing, understanding what the question is, what the user prompt is, and then generate an output to hopefully answer that particular question. And so you've often heard probably the term, hey, language models or large language models are like just next token prediction engines. And that's actually true. And that's no different for small language models. And kind of the difference between the two is that a small language model is you require fewer resources to run, and that's by intention. Kind of the idea is instead of having massive GPU farms where you're like serving up large language models, you want to have small language models run on like modest hardware and maybe even potentially even CPU. And there are many CPUs out there that actually have acceleration engines to do floating point calculations where you don't need a GPU. They're mainly used for inference, but lower end GPU or even CPU. And the end goal is to have a good quality output, faster inference, because if you're not requiring like massive amounts of expensive GPUs like an H100, faster inference, and of course, because you're not using a very expensive GPU, you have lower costs on your infrastructure, right? Commodity CPU or less expensive GPU. And by also extension, because you're not using these super powerful GPUs, right, you're saving on power, you're saving on cooling, you're saving water, all of those things. And that is what a small language model is. So kind of for our project today, what we're building, this is kind of like our mental map. We're going to build a nano GPT style causal language model from scratch. And in actually even just machine learning models in general, but even building large language models, you have kind of, I like to say, like 4 steps that are required. And these are the 4 steps. You have some form of data preparation. You take the data set. Do you need to massage it into some format that's familiar that can be used for like something like PyTorch? Then you have a tokenization process. So we need to basically tokenize the input or this data set into something that can actually be operated on by like PyTorch or any other machine learning framework. Then we have a training loop. We go ahead and we iterate over and over and over again over the data set. We save our model, and then we deploy for inference. So these 4 steps are what we're going to talk about next in some more detail. So typical GPT model architecture, generative pre-trained transformer model. So this is kind of like just the blueprint, and I've intentionally made this presentation and the slides kind of wordy because I'm a visual person. If someone says a word to me, it usually goes in one ear and out the other. So you can be able to like see the words as they're being presented. And also it actually helps out AI chunking so that it can be consumed by AI and it'll be easier for it to read. Anyhow, so you have your input, so you have your data set. You have, that data set is, since we're talking about language models, that's in text, a whole bunch of text, and that's our input. Now what we need to do is we need to actually convert that into IDs. And the text are converted into token IDs. And that's done by our tokenizer. Now each token ID becomes a vector, right? If we're transitioning and trying to predict the next token, right, we have to have a means of understanding how important is that particular token to the next one that we're going to append to our answer. But in order to do that, we need to have something called attention. And what attention does is we basically take a look at all of the tokens that came before it, figure out all of the context that's associated with it to determine what the next token, the best next token should be. And that's what attention is, the ability to go back and take a look at all of the tokens that came before it to decide what the next token should be. Now, you might hear this term called transformer. So transformer is, if you're going to look back at all the tokens that came before it in order to find out what the next one is, we probably don't want to do that one at a time. And so what a transformer allows us to do is think about it in computer science terms like threads. You want to be able to calculate a whole bunch of these, I think the next best token is, in parallel. And the key word is parallel because that's what the GPU is for, right? So that I can figure out how many different lanes of prediction for the next token, what I think is going to be the next best one, the most probable one. But I also want to be able to predict many of them in parallel, just in case one is better than the other. We don't want to commit to just one. We want to run a whole bunch of them in parallel in one shot. Now that we have all of these lanes, right, we have one lane that says this token's the next one. We have one lane that says this token's the next one. We have one lane that says this token's the next one. How do we know which one is the one that we say, this one is probably the best one to use? So that's what the prediction head is. So it's another term that just basically says we have the state of all of these threads or all of these parallel next token predictions, and we need to rank them. And we need to rank them to which one is the best, which one's the next best, the third best, the fourth best, and so on. And if we just take the top one, like top k equals 1, that gives us the next token that is the most probable to be appended to all of the context, all the previous tokens that we've generated prior to that one that we're adding to the end. Now, got a new token, appended it to our answer. Now we have this thing called an autoregressive loop, which is just a fancy way of saying do that over and over and over again until you get your answer. And so that is literally the process of how a large language model or a small language model works internally without requiring a PhD. So in a small language model, why is it small? So it's small because you're intentionally, right, going from a large language model to a small one, you're intentionally lowering the parameter count. So you hear large language models, 100 billion parameters, 200 billion, trillion parameters that are coming out. And large language models are going to be massive. But for small language models, you're talking around 4 billion to 8 billion parameters, which therefore translates into I don't need ridiculous amounts of GPU memory and resource in order to run the thing. The context window typically can be smaller, although that doesn't have to necessarily be true. And then, you know how we talked about vector, like we have a token where we're at, and we have a vector. We're going to decide what token is the next one, whether it's in this lane, or this lane, or this lane, or this lane. In a small language model, the number of lanes are reduced, but they happen to be the most probable lanes. So the things that we're starting to lop off are things that we really don't care about, right? The things that are not as probable. And so the number of next token transitions of the next vectors is reduced. So what that ends up translating into is the reasoning capacity. So that's a typical GPT-style large language or small language model architecture. So that's kind of like the process of how a large language model works. So for the data prep portion, right, we need data to train on, to build and to understand language, to build a small language model. So you need a ton and a ridiculous amount of data. And so for the Nano GPT style small language model that we're building, I considered 2 data sets. One is tiny stories, which is, the link is there, you can go ahead and look at it. It's about a 1.6 gig in size. And then the one that I actually ended up choosing was FineWeb EDU, which is a 10 terabyte data set. So massive, right? And I have the link to it here. And the reason why I picked that one is actually not ideal that I picked that one, but I picked that one intentionally. So you can click the green link there. There's an entire paper on Hugging Face that discusses the FineWeb EDU data set. And they analyzed it, and so some data scientists analyzed it and said, these are all the things that you need to curate to make this data set like really clean and really powerful and really usable with like the least amount of problems. And it's very fascinating. Go ahead and read it. But what a data set, in practice, what it does, you need to divide it into 3 different categories. One is training, right? Training data tends to be the most massive portion of it. And then you have a smaller validation data set. And so what you do is you use this training data, and then you go ahead and you look at the validation data and say, how far off am I when I'm training this thing? And the idea is that you use the validation data set to get it, to push it in the right direction so that it accurately captures what you're trying to build, in this case, a large or small language model. And then you typically, although it's not really super true in large language models, there's usually a test data set that just, you feed in test data and find out how far off you are, what is the confidence score, and how far off am I from the actual thing that I'm trying to train. So, tokenization, right? Computers don't do text. So, how does this actually work? A tokenizer, all it does is, it takes, there's actually many forms of tokenization, there's 3 of them, but what it does is it replaces words to numbers. And so the simplest example is this word piece tokenizer. It just tokenizes for every word, like the word like the or cat, and then it takes cat and it assigns it an ID, a unique ID, and that unique ID represents cat. And it doesn't need to know what cat is, it's just this ID. And anytime you see the word cat, it just references that particular ID. So it's just assigning a number to a label or text in this particular case. And those numbers end up becoming like the alphabet for your language model. And it's very important that you don't mix your tokenizers. So kind of like the computer science way of thinking about it is you have maybe a file that's encoded in UTF-8. If you save a file in UTF-8 format and then you try to read that file in Windows Unicode, that's not going to work well for you, right? It's going to look like garbage, and it effectively is the same thing for large and small language models. You can't mix your language. And there's also another much higher level way of thinking about it, like mixing Spanish and English. Totally different context, but you can't chunk on different tokenizers. So we talked about the data set, talked about the tokenizers, now the training process. So I kind of already alluded to it a little bit. So we train a model, we take that training data, and we go ahead and we test that training data like against that validation data set. And then we basically say, hey, how far off are we from the answer? And then we adjust accordingly. So that adjustment, if you think about it, if we're training and then we need to adjust, we want that number or that adjustment to be as small as possible. Because ideally, in the best case scenario, if that adjustment is exactly we don't need to adjust at all, that means we've found our answer, so our adjustment is 0. So when you're training language models, you actually want that value to be close to 0 or near 0. The smaller the adjustment, the better your machine learning or your model is learning at a good learning rate, and it's actually doing what you are predicting it to do, right? Give you quality answers. And that is done through a loss function. So the loss function is basically, hey, I'm going to take the training data, look at the validation data, and then find out the difference. And that lower number, we're going to use the loss function, and that lower number is what's going to say, hey, this is what I'm starting to see patterns in the text and the data that is there for the language model, and I'm going to go ahead and say, okay, we're on the right track to building a language model that understands language. So now we've built, after we've trained our model, we have our data, we've done validation on it, and we're going in the right direction. Basically our loss function says that we're getting closer and closer to honing in on understanding the structure of the data set, which is effectively just learning a language. And once we get to the ability to say, hey, this language model can now understand the context or the domain of the data set, we're going to go ahead and save it. And that can be done in like PyTorch checkpoints. That could be done as Hugging Face, Hugging Face binaries or checkpoints, safe tensor format. It could be, if you're using like Onyx, it could be like a bin format. So you just export it and save it so that you can run inference on it. But it's very important that as you understand that as you're training a language model, it's picking up subtle nuances at every step of the way. So it's understanding like the association between the previous word that came before it, the next word. It's looking at the context of that word in sentences, and then it's looking at that context in potentially even paragraphs, right? Depending on how you architect the thing. But at the end of the day, you have a language model that's been trained. You have, as you start to spit out the answer, you look at all the tokens that you spit out prior, you try to predict the next token, and then you append it, and it's effectively a list of tokens. And who here has heard about top K, top P? Okay, oh, cool. So if you have a list of next possible tokens, your ability to manipulate what that next token is using like top P and top K. And what those are, I'll just say really briefly. Top K is only show me the next 10, or the top K is only show me the 10 most widely used tokens. And top P is show me the, like, if you use like a top P of 10, show me the top 10 most probable tokens. So that gives you your ability to manipulate what the next token can be. So let's do a little review here. So we take text, we turn them into token IDs, we take the token IDs and the goal is to generate vectors. We have this attention mechanism that says, hey, I can go back and look at all the previous tokens that I've generated before. I want to have run multiple parallel lanes for what I think the next probable token can be. And all of those lanes, I want to say which one is the top one, which one's the second one, which one's the third most probable, which one's the fourth. And then do it over and over and over again, right? Keep appending the next token to the next token to the next token. And so if you try to build out this large language model or the small language model, and you try to build it like a machine learning model problem, it actually goes really bad. And I knew going into this, like why this is, but I was just kind of curious to see how it would fail. And how it will fail is you will run out of memory on your GPU. Because you're talking about a 10 terabyte data set, and you cannot possibly fit 10 terabytes in the memory for a GPU in this particular fashion. So typically a machine learning model, so not a large language model, just a strict machine learning model, you make a pass over the data multiple times. So if I'm trying to take 10 terabytes and do multiple passes over and over again, that's not going to work out well because it's 10 terabytes. So how do you actually go about building one then? It's definitely a lot easier said than done. And if you're trying to build a GPT-style large language model, first, a single H100 is not enough. You will be there forever, or even an H200. I started with an H100 just to see like what would happen, and it almost immediately crashed out. Not enough memory, as you saw from the error log, because the data set's too large. So I had to switch to a node that had 8 H100s. And as you can imagine, this gets pretty expensive pretty quickly because I'm using 8 H100s. And if you go on to like DigitalOcean or Lambda Labs or whatever, you're talking about anywhere from $24 to $28 per hour for this node with 8 H100s on it. And because the data set is so large, it will take thousands of hours to train this small language model. So for the first demo, I obviously did not let it run to completion. And we'll see first, it's expensive, but we'll see kind of like what the effects of that, kind of like the fallout of that is. So we already know the data set is way too large. We can't do multiple passes over the data set and load it all into memory. So how do we take this FineWeb EDU data set that's 10 terabytes and deal with it? And so what you have to do is you have to change to a streaming token data set. So this is actually the interface for Hugging Face. I actually intentionally use this interface where you can actually stream it directly from Hugging Face to feed it in a stream format to the 8 H100s to break them up, to parallelize the process. It's pretty interesting going about doing that. If you're looking to further speed that up, it turns out like the company I work for, NetApp, they deal in storage. So we actually offer a couple solutions to help enhance and speed up that process. But suffice it to say that since you're streaming this data set, you have to be able to dynamically break apart some chunk or some portion of the data for your training data, and then you have to dynamically, as you're streaming in data, have some of that data reserved for your validation data set, right? Because we've already kind of just said, you need training data, you need validation data, and you need test data. So you need to do, as you're streaming, you need to do this dynamically. And so now the problem becomes a little bit more difficult. And who's heard of like epochs? Like when you're doing machine learning models and you're training and you have one epoch, two epoch, right? So what that means is, oh, yeah, cool. So that epoch, what it means is you are doing one complete pass over the data. And so when you go to the second epoch, you're starting the second complete pass over the data. Well, we just said that we can't do that when we're training a small language model. And so we can't use that method. So what you have to do then is you have to use a step method, which basically, because we're streaming that information, we're basically streaming it and doing it in a stepwise method. We're going chunk by chunk by chunk by chunk by chunk by chunk of the data set. And so we're effectively doing batch processing because we can't load the entire data set in memory all at once. So I abandoned, obviously, the naive way of doing it, which is trying to load it onto an H100 using loading the entire data set into memory. That didn't work out well. If we take that data set and then we have this tokenizer called tick token, it actually happens to be the OpenAI GPT-2 pair byte encoding tokenizer. They open sourced it, and we create based on our data set, we create a vocabulary of 50,000 words, right? So each word becomes an int or a token ID. It's like flipping back and forth. So that becomes our vocabulary, 50,000 words. And we can actually also use the GPT config, which is also OpenAI's configuration for like a block size of 2K. So that's our look back window. So our look back windows are attention, like how far back can we look for tokens. Then we have, this configuration also defines the number of layers. So this is our transformer block, right? How many things can we run in parallel? The head, which is how many, so 32 different evaluations of the lanes. How can we evaluate each one to say which is the best one for the next token? Then we have the vector dimensionality. Each vector transitions to another vector, and we limit and cap it at 2K. And if you do all of those things, use that tokenizer, use that configuration, and then use the FineWeb EDU data set, you roughly get a 1.8 billion parameter model, which in today's world is sad. And it's so sad, I'm going to demonstrate it here right now. So you don't need to write any of this down. The code's all available in my GitHub. I'll show you the link to that repo at the end. You can do this at home. But to start off the training process, you can just go into the small language model folder, go Python 1_train 8x H100. That will stream the data set, do the training process, but it does require 8 H100s. And I stopped it at 10% of what is required to actually train that thing to completion. And the reason why is it got ridiculously expensive. I was footing the bill for it for this presentation, and yeah, it was not fun. So I intentionally stopped it early. And by intentionally stopping it early, this is what the output kind of looks like. So just like any kind of language model, you give it a prompt, and the prompt I gave it is kind of like a story. And the prompt is, it's loading. I'm doing this on my local laptop just to kind of prove that. And this is an M1. And I know like the M3 is got additional floating point calculation, so it's much, much faster. But I'm intentionally doing it on a slower laptop so that you can see that you can actually still load it in memory and run it. So we're doing a story, once upon a time in Long Beach. That's where I'm actually from. So I'm from Long Beach, just down South LA County. And we want the small language model to basically complete this story and give us, do the completion of our bedtime story. And this might take a little bit of time here. Once upon a time in Long Beach in the time of the year 1815, blah, 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 complete, utter garbage. And it's because I stopped it early. And yeah, it's absolutely horrible. So, and this is intentional, I knew this was going to happen. So, obviously, when you use a large language model, even a small language model like Llama 3, 8 billion parameter, you actually get a coherent answer, and this is definitely not it. So why did I do this? So a GPT-2, right, now we're at OpenAI, actually 5.4 came out today, right? Yep. So even training a GPT-2, like version, small language model, is ridiculously expensive. It requires, if we remember that data, that Hugging Face data set, that paper, it actually requires 6,000 H100 GPU hours in order to train this model to completion. And if you do the math on that, the estimated cost to like run this model to completion, which I'm not going to burn 20,000 K to just show you this model and how it is, it will be 20,000 K per hyperparameter, which then gets you to the roughly 8 billion parameter model that you would typically see in a small language model. So what is the takeaway of this? No person in their right mind does this, right? Okay, thank you for attending. No, I'm just kidding. That would be hysterical. You have learned nothing. Okay, so it costs too much money, and the resource, 6,000 H100 hours is ridiculous too. So kind of the takeaway is there are very few people or companies or individuals that have access to the resources that do this. It requires a lot of resource, a lot of cooling, a lot of power, a lot of water. So that's because it's a hard problem to solve. And if, we're not going to play the video, but if you want the actual PhD version of explaining all of this, and actually what the code is based on, so who knows this particular fellow? Andre Kaparthi, awesome. Former OpenAI, former Tesla, and then I think he went back to OpenAI for a bit, and now he's starting his own thing. This is a 2-hour tutorial on how to do it in the PhD way, but I gave you basically the non-PhD way of doing it, but it's a really cool video if you're interested. And you don't need to take a picture of the slides are also in the GitHub repo too, so you have all of it. Okay, so I told you that's not the way to do it. How do we actually do it? And this is the recommended way. This is what you actually want to do, is you want to fine tune an existing model and impart the knowledge that you want to impart on it, and then optionally quantize it, which basically, we'll talk about it in a little bit here. So this is a much easier way. Not only easier, but far more cost effective, and we'll kind of look at that. So what is fine tuning? So fine tuning is taking an existing model, and in our next demo, we're going to use Qwen 2.5, the 7 billion parameter model. But we're going to take a model that's kind of a generalist model. Now, if you just need generalist kind of language understanding, you can stop right there. You have all of these cool models that are available. You can just use it to understand the language of your choice. But if you want it to have some sort of specialized knowledge, then you need to, on 8 billion parameters, it probably hasn't been trained on that specialist knowledge. And that's the reason why a lot of people go to these massive, trillion parameter models, is because they've been trained on the world. But it's also very expensive to run on your GPU, right? And like GPU farm, right? So the alternative is to take a small language model and impart the knowledge, the pieces that you actually care about, and impart that behavior onto a small language model. And so that's exactly what fine tuning does. We're giving it a new data set. We're modifying the weights on an existing model, and we're imparting that knowledge onto that model. But all of the mechanisms that I talked about, predict, compare, and adjust when we're doing the fine-tuning process, they all apply to fine-tuning as well. Slightly different process, but it's still the same thing. Predict, use the validation data set to push it in the direction that I want it to get, and then adjust as necessary to get it to build a model for your specialized particular knowledge. So the non-data science way of saying, think of a GitHub repo. You have a GitHub repo, a project, a probably cool project that you say, this is really cool, I would like it to do something vastly different. I'm going to fork that repo, completely change the behavior of it, but like most of the skeleton's actually pretty good, but I want it to do something else. And you want it to do that one else, that one special thing. That's exactly what fine-tuning does to large language models. Fork a repo, change the behavior massively to do one thing really, really well in particular. So who's here has heard about quantization? Okay, cool. So when you train a large language model or small language model, typically it's done using floating point 32. And the idea of quantization is, instead of using floating point 32, we're going to use different numeric representation, right? Because everything becomes an integer or a number, sorry. And we want to change the math of the problem to something that's much more manageable. So you can quantize a model that's using floating point 32, and you can quantize it down to like int 8, floating point 16, and then BF16 is this one special thing that NVIDIA does where, I always mess this up, but like the precision is less and the numerical value is larger. Anywho, it's a different representation of a floating point number. So what are the, like, why do you do this? So smaller memory footprint. Instead of using 8 bytes for FP32, if I'm using int 8, I'm using a fourth the number of bytes. And just by thinking about the math on that, you're using a fourth less memory, like 1/4 of the memory that you were using into int 8. And so you're basically effectively making the math much easier. Now, some CPUs or GPUs, well, some CPUs, they're not really good at floating point. So you convert the math to int 8, which every CPU on the planet knows how to do integer arithmetic, right, or manipulation. And so that's the reason why you change something to like floating point to like int 8. And that, now you can run that particular model on commodity CPU hardware. You don't require as much memory to load. And that's the whole purpose of quantization in a nutshell. So I'm running out of time. So what doesn't change? So there's a bunch of things that don't change. You're starting with the base model, so all of the characteristics that you normally have, you still have all those same characteristics. So like the context window, the attention heads, the layers, and all that stuff. Fancy way of saying you're just changing the behavior of the knowledge that you're imparting onto that model. I'm going to skip this in the interest of time, but there are 3 methods for quantizing. The last one's really cool. I'm just kind of like lopping off and I'm using the most pertinent, so you're kind of like lopping off and removing the stuff that's the least used or the least, yeah, just kind of like leave it at that. So because of the quantization process, before quantization require much larger memory footprint, you need a GPU, the inference speed is slower, and then the correctness is actually really high, right? Because you're using the full-blown power of a GPU. After quantization, the memory footprint's lower, processing power, you might be able to get away with a CPU or a low-end GPU. The inference speed is much faster, and the correctness takes a small hit, but don't worry about that because it's not actually, if you think about it, because you're imparting specific knowledge onto that existing language model, that's what you care about, and that's kind of like you're pushing the weights in that direction, and you're removing the stuff that actually you don't care about anyways. So the process is very similar. Start with just a review. Start with an existing model, and in our demo, we're going to use Qwen 2.57 billion parameter. You have a data set, you fine-tune it, and then you validate it, and then you deploy it. So the model we're going to use is a SQL small language model that will understand how to generate SQL statements and understand SQL statements. So that's what we're building. Qwen 2.5, the data set is a database schema plus a question, and then the output is SQL. And so that's what the data set looks like. We're going to fine tune it. There's a fine tune strategy called LoRa, don't worry about it. And then we're going to quantize it down to int 8. So let's go ahead and take a look at that. If you want to do the training process, the fine-tune process, that's probably, you can see Python fine-tune, run that. It will automatically load the data set and start the fine-tuning process on Qwen 2.5. If you want to quantize it, run quantize. It will take the final model that gets produced that now understands SQL. It'll quantize it down so that you can run it on a laptop. And we are going to run inference on it right now. Oh, shoot. Oh, Python probably doesn't work, right? OK. So this is we fine-tuned the model. We've imparted the knowledge of SQL. And this basically, don't worry about the warnings and all that fun stuff. So we basically, as a part of our question, we're going to ask our new SQL language model. We're going to give it a table. It's a simple table, right? Create table, persons, or employees. And it's going to have like the person's name. It's going to have like their age or whatever. And we're going to ask it some simple questions. So the first one we're going to ask is list all the usernames in this particular employee table or this user table. And it's going to, because now our small language model knows and understands SQL, we can actually get, this is actually dynamically generated, right? This is the response from our particular language model. Select name from users. List all the names for users. Who is the highest paid employee? And so how would you write that in SQL? Anyone want to take a stab at it? Select asterisk from users, order by salary, descending, limit 1, right? That's like one way of doing it, right? Hopefully it will come up with that. Yes. So we literally trained a small language model that can answer SQL problems for us. Pretty cool, right? So that one, oh, right here. So the cost to train that model, $100. I think it was far less than that. I think it was like ended up being just under 100, or maybe it was just over 100. But versus $20,000, right? So if you need special special knowledge, like SQL, imparted onto a small language model, this is how you would go about doing it. This is a much better way, much cheaper, much more effective, and if you want to quantize it to run on commodity hardware, this is the way you go about doing it. And what's really cool about this approach is if you're starting with Qwen 2.5 and you need to iterate over your data set or your training, or maybe there's a new version of SQL that has new language statement or whatever, you can just rerun it and it's totally iterative, right? Start with the model, add the new data for the data set, do the retrain, and start that way. Real quick, because I got one other section. So the question was, how big was the data set? I kind of really did gloss over it. So it's a synthetic text to SQL data set. It's publicly available. I can't remember the size. I think it was actually on the order of, tens of megabytes. Oh, just click it. It was, no, definitely not terabytes. It looks like 32 megabytes. Now you know all the links work, right? So much cheaper way of going about this. So cool, we built a SQL language model. But it actually is kind of, this is the bonus section. There are actually many types of language models. It's not just the Q&A one that we're used to, where you ask a question and you get a complete answer, like, tell me the difference between a cat and a dog. GPT runs around and says, this is what a cat does and this is what a dog does, right? There are many other language models. And here are a small list of them. So there are language models that do summarization. There are language models that do code generation, which we just did, right? SQL, that's code. And our next demo is going to be this MLM. So it's a masked language model, which we'll talk about in a second. There are classifiers. But kind of the idea is, if you have a particular language specialized language domain that you want to impart onto an existing language model, you can teach it to do things. And I'll talk about one at the very end when we get to resources. But a masked language model, so who here, oh man, I'm gonna date myself here, right? Who here remembers Mad Libs? Yes, right? You had sentences, you had blank spots, and you had to fill in the word in that blank spots. The idea is to make it super funny by picking wacky words, but you basically have sentences with a gap in it. Now, what a masked language model does is it actually, based on the sentence that you're providing it, it will actually guess the most probable word that should fit in that particular gap or that hole. And so that's kind of exactly what a masked language model does. Now, there are a whole bunch of applications that you can do for it, like you can do extraction. I know that sounds weird. You can do classification using a masked language model. Basically give it a string and say, classify this. It should be blank, and it will analyze the sentence and it'll give you the most probable classification for it. And there's also this question mark, question mark, question mark, and I'll tell you why that's there. But let's just get to the demo. So the last language model demo, we're going to do the masked language model. So just like before, if you want to train it, this does the data preparation step. This does the training, and let's run inference on it. And it's actually, this one's super quick because we're only trying to guess one word in a sentence. So the capital of France is blank. And based on that sentence, we ran it through our masked language model, and it said the most probable word is Paris. The capital of France is Paris. And then distilled models are the blank of large models. And then the most probable word is smallest, which is correct. So that's what a masked language model does. Pretty cool, right? So I'm kind of floating the idea out there. You can do all sorts of wacky things with language, and there are many other forms of language models out there. This is one example. So I actually have another session tomorrow. It's actually pretty cool. It's this one right here. And I'm going to tell you why I built that model, and I'm going to use it in this session right here. But if you're interested about doing side channel acoustic attacks for keyboards, so think keystroke loggers based purely on sound alone of when you hit a key on a keyboard, can you guess the letter that's being pressed just by the sound on it alone? And spoiler, you absolutely can. But if you're interested, check out the session tomorrow, 101, room 101, I think it's at 2:30. So resources. All of the code to build all three of these language models, I would recommend not doing the first one. If you want to burn a whole bunch of money, go for it. Otherwise, the two useful ones are the last two. But they're in my GitHub repo here. All the code to do the data prep, the training, the fine-tuning, quantization, and all that fun stuff is available in my GitHub right there. So why do we care about this? Why am I talking about this? You've probably heard this tokenization explosion and the cost that's associated with it. The reason why we care about small language models and the reason why we care about quantizing them to run on cheaper hardware is that, if you think about OpenAI, they're losing, tens of billions of dollars a quarter or something now. And then I'm sure Anthropic is probably on there too. I mean, if they're losing money, you're getting your tokens on a discount right now. And imagine over time, you're probably competitors are going to drop off, and at some point they're going to need to show a profit, and guess what's going to happen to the cost, right? Do the math. So quantization and running small language models like on your laptop or on cheaper hardware, that's the reason why you do it, right? Cheaper power, you don't need as much power, cooling, inference, and all that fun stuff. I have a blog post about it, and I'm actually talking about using small language models in an agentic, multi-agent, agentic AI setting. It's actually in April at Open Data Science Conference East. NetApp, we do storage, and if you're looking to stream data from data sets to train your large language or small language models. We have a couple of solutions. You can use Kafka and all that fun stuff. I need to do the company plug so they will pay for my hotel room. But we do that, and I would highly recommend you take a look at it because it does help the training speed and cost like way better. But yeah, cool, thank you. I think we have time for questions. Yes, I'll try to repeat the question.
So I agree that the training the small model takes lots of money, and even training the fine tuning takes some money and time, more importantly time. But the same thing like you demonstrated that coding can also be achieved by agentic AI. We provide the tools to query the database, so if the orchestration there comes, it looks at what are the tools I have. If I have a tool to query, it will query and get it without paying anything or losing any money other than the token you pay for the large language model. So how do you compare the fine tuning or the time versus writing that Python code agentic in a couple of minutes to achieve the same thing?
So basically, I'll summarize the question, like why fine tuning and why not just use a model that's well, agentic, who's that language model exists somewhere. Where does it exist? So if it's running on OpenAI, one, anything that you provide in the prompt, anything that you're providing as a terms of like embedding data, you're providing that to OpenAI. If you're okay with them having your data, go for it. Now, if you can run in your own like GPU instance, like an A100, you don't need to go for a huge H100. But if you can run that using like a NeoCloud or Google or whatever, but like run the model yourself in your own infrastructure, one, you have data privacy, which is huge, right? And then two, like, I guarantee you at some point in the next year or two, the cost of OpenAI is going to just skyrocket, right? And if you can build out your agentic solution using models that you can run and predictably understand the cost of running that model, I think you'll be in a far better position, right? Because right now, there are people that are using like Claude Code, right? And I know people that are spending like $300-400 a week on Claude Code. And that's great. Like, trust me, I use it too, by the way. So I use Codex, I use Claude Code, but it's getting up there, right? Now imagine when they actually start to crank up the cost on all this stuff, and it's going to get far more expensive, right? Now, if you so in the Open Data Science Conference talk in April, actually, it's that agentic AI talk. I forgot the name of the title, even though I wrote it. I'm going to actually take that the SQL model that we just built today, and I've already built a Python small language model so that it understands Python. And I guess the spoiler alert on the demo is I'm going to take those two models and use build out a small little agentic system so that it says, hey, if I want to call a Python SQL, or if I want to call a SQL statement against the SQL, like MySQL or whatever, in Python, that is the demo that I'm going to show in April. But I can predictably understand the cost of both of those because it's a small language model that I'm actually going to run on my laptop, right? Versus potentially, running into, I think there's many companies out there that are starting to run into like $30,000, $40,000, $50,000, $60,000 in token costs per person, which that's starting to get up there, right? So kind of the idea is run it on your laptop, run it in your own infrastructure. You can predictably understand the cost of what's associated with it, right? Yep. Any other questions? Question? Oh, right. Yep. I don't know where the microphone is. I'll repeat it. Yeah, go for it.
So if I understand correctly, what you said, fine-tuning, it's kind of the same as training? Oh, right. So if I understand correctly, fine-tuning an existing model, it's kind of the same operation as training it, right? It's just that you're doing it on top of what is already trained.
Yeah.
do you need to use the same loss functions, or can you pick a different one?
It kind of depends.
In another way, how similar does it need to be to the original training?
It doesn't have to be. Like, however you need it to be to have it impart the new knowledge on whatever it is, whatever domain it is. You don't need to know how the base model was trained in order to do the fine-tuning on your new model. And I guess I should also probably say, which might be the next question, is like, why do I fine-tune a model versus use RAG with vector embeddings? So I didn't cover this, and I probably should have. So why you fine-tune versus using RAG? So if your small language model, that's just that base Quen model, if all you need it to do is understand language, you can stop there. You can feed it data. You're not using any kind of specialized thing, like specialized domain like SQL statements. You can just have and use RAG, get your vector chunks, take the chunks, feed them into the prompt, and say, based on the vector chunks, tell me about the answer that you're, sift through the data and tell me about the answer. So that's what a RAG pipeline is, right? I'm taking data, and I'm just having the language model sift through that data in order to find the answer within the data that I'm providing it. Now, a fine-tuned model, you're trying to change the behavior of the model, and that's the difference. That small language, if I started giving SQL statements to Quen 2.5, it would probably barf on me and say, I don't even know what you're talking about, or maybe, in the worst case, start to hallucinate something and say, I don't know, dog, cat, blah, 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 right? It doesn't know that stuff about SQL. So what you're trying to do is you're trying to change the behavior of the language model to say, I want you to know about SQL now. And that's the difference between the two.
Thank you.
Yep. Any other questions? I think we might be running out of time. 3 minutes, right?
Yeah, so based on what he already asked and
Yep.
partially already answered, you can run 7 billion parameter model on local laptops. And if they jack up the price in next year, rather wait for the M3 or M2 price to go down as the Apple come up with more, and use the whole model, 7 million parameter to run on a local laptop M3, by that time price will be cheaper. So why not use that approach? But as you mentioned, even that would be not as good as training it for the specific skill set what you mentioned. Is that correct?
Yeah, so okay, let me repeat the question. I kind of like to digest it. So like, why use Quen, like a 7 billion parameter model versus like a whole, like larger model or a different model, right?
No. So you said you train it on a 7 billion parameter
Yes.
model and run it faster with the skill set. So if you don't do the skill set, wait for a newer version of that, maybe 9 billion parameter next year.
So like,
what's the...
yeah. So I used Quen 2.5. 3.5 just came out a couple weeks ago. It still doesn't know SQL.
Oh, okay. So it's still, training is still worth it. Okay.
Yes. So even you have a new model come out, it's a very general purpose model, and it probably doesn't know anything about SQL. So even when that new particular model comes out, you still need to teach it SQL.
Okay, so in the follow-up question, so you can teach, even though it's dumb in answering SQL, you can teach the base model to have special skill set. That's what the whole point is. Okay,
You got it.
Thank you very much.
And then like the cool thing is, like, because the training process is the same, when the 3.5 comes out, you can use 3.5 as your base model, rerun the script to train. Now you have a 3.5 model that maybe understands language a little better, but now also understands SQL a little better, right? Yep, cool. Anywho, I think that's my time, but if you have any other questions, I'll be outside. Thanks for showing up.